Alright, the first half of the first lecture is going to be on mechanisms of chemical reactions. And I've got most of this typed up, shouldn't be too bad. And the first slide here is just some general information about mechanisms. We went over this in class. You can have the overall reaction. Oftentimes on tests they'll put it in a box. And then you may need to guess some kind of mechanism in order to be able to determine what the overall rate law is theoretically and see if it matches the experimental rate law. Remember, I told you before that you cannot use the coefficients in the balanced overall reaction to determine the rate law. But here's a way using the mechanism to figure it out, to figure out what the rate law is and to see if it matches the experiment. So we went over some of this before. We've got the IO minus in this mechanism, which is formed in the first step and then consumed in the second elementary reaction or second mechanistic step. Therefore, that's going to be the intermediate. On the other hand, we've got iodide, which is present initially. It changes the rate of the reaction and the mechanism, and then you end up with the iodide at the end of the reaction. So in other words, it's not consumed. That's going to be a property of the catalyst. And notice in the overall reaction, the IO minus intermediate has been canceled out. It's not given, but the I minus catalyst species are present in the overall reaction. All right, now we talked about the molecularity of each of the mechanistic steps. It's the number of reacting molecules on the left side of the arrow. So in both cases, there are two species. You've got, let me get another color here, yellow maybe. So you've got two species on the left in step one, therefore it's bimolecular. And then purple, you get two on the left in the second step, and so the second step, mechanistic step, is bimolecular as well. So they're both bimolecular in this example. Alright, now there are two mechanisms we're going to look at. The first one's easy, the second one is much harder. And we're going to use a reaction that has an overall reaction. 2NO2 plus F2 forms 2NO2F, and it is gas phase, not critical, so we don't want to drag around the parentheses G on every species. Just write it and forget about it. It's the gas phase. Now, from experiment, it was determined that the rate law for this reaction is K times NO2 to the first power, and F1 to the fluorine F2 to the first power as well. So you know how to figure that out. If you leave the concentration of fluorine the same, double the concentration of NO2 here, and then the rate doubles, you know that that's going to be first order. You do the same for fluorine. That's how you figure it out from experiment. Okay, then you add up the individual orders to get the overall rate law, which is 2, so we say it's a second order rate law overall. All right, same reaction, next page. We can guess that the rate law would be that rate equals K times NO2 squared and F to the first power, just a guess. If we looked at the overall stoichiometry on the last page, it's a 2-to-1 reaction. Maybe you would start with that. This turns out to be wrong because 2 plus 1 is 3. We know that the reaction is second order. So it's wrong. But it's a good guess. It's a good start. So instead, we can come up with a mechanism that will possibly be a better choice. It's going to have two mechanistic steps, the slow step and the fast step. Let me use a pointer here. The slow step and the fast step. And then they should add up to the overall reaction. So here we have the first NO2 is going to react with an F2 to form this NO2F product plus F. Okay, F in this case is going to be the intermediate. Once it's formed here, then it can be consumed in the next step in the mechanism to react with the second NO2 molecule to form the second product molecule. So in the end, the F's are going to cancel. Those are the intermediates. You add it up and you get the overall reaction, which is on the last page. So the mechanism looks good in terms of the stoichiometry. All right, so then the next step is to look at, this is just a principle in kinetics that we use when writing rate laws, and it's in red here. The rate of the reaction equals the rate of the slow step. Okay, we're going to use that idea. And one analogy that I'll use in class sometimes is me driving from Thousand Oaks to CSUN to get to work in the morning, and I tend to go kind of fast. But let's say that I encountered some car accident on the way, and it just took hours to get through that bottleneck. So you could maybe think about 3 parts of my trip. The first part, I'm driving quickly down the freeway. I get to the accident. Now I'm going very slowly, and then once I get through it, I speed up again. So, you know, if it were hours and hours to get through that car accident scene, then you would say the rate or the time or the rate at which I get to work really is going to depend on that slow step. And it's that way with chemical reactions. There can be many steps in a chemical reaction. One of them being slow could be thousands and thousands of times slower. So it's just an idea that we use, and we say the rate of the reaction is going to equal the rate of the slow step. So now you just, whoops, hang on, smaller pointer here. Now you can just write the rate of the slow, here's the slow step. You say rate is equal to K1 times NO2 times F2. So in theory, I could have put a K1 there, but then we say K1 is equal to K overall for the overall rate. Okay, so this is correct. It does match the fact that it's second order from the experimental rate law. So this is correct, and that is the answer to the problem. We just take the slow step and write the rate law from that. All right, now there's another mechanism. I labeled it 2 here, and this one is a lot tougher to get through, but we use the same principle, that the bottleneck principle, which states the rate of the reaction is equal to the rate of the slow step. So we have an overall reaction again. We've seen this one before. This is the N2O5 decomposition to form 4 NO2s and O2. And remember, we looked at this in some detail and definitely came up with a rate law based on experiment that is first order in N2O5. Remember, we doubled the concentration of N2O5 and the rate of the reaction doubles. Excuse me. All right, so this is the information from experiment. We know that it's first order. Okay, now, because the coefficient in front of the N2O5 is 2, we might have guessed that the rate is equal to K times N2O5 squared. Okay, so that's just a guess. We know that it's wrong because experiment tells us that this is a first order reaction. So instead, we're going to guess a mechanism, we're going to devise a mechanism, and figure out one that's consistent with this overall process. And by the way, on a test, I'm not going to have you guess mechanisms. I'll give you mechanisms, and you have to work out the details of them. All right, now here's something new. We haven't talked about equilibrium yet this semester, but it is one of the main topics of the course. And let me get my pointer. This symbol with the rate constant K1 on top and K negative 1 being the reverse rate constant, the rate constant for the reverse reaction here. that is the symbol that we use for equilibrium. So you put the rate constants above and below to indicate forward and reverse reactions. All right, now equilibrium means that at any point in time after the equilibrium is established that there's going to be a certain concentration of N2O5 and NO2 and NO3, and if the system's at equilibrium, those values should be constant. All right, now what happens, this happens quickly, so the concentrations of N2O5, NO2, and NO3 are established, and then in the next step you can see that the NO2 and the NO3, instead of going back to form N2O5, they go forward now, they react to form NO2, and O2. All right, and then once the NO is formed here, it'll react with any NO3 that might have been established in the first step. So in the third step, we get the NO3 and the NO combining to form to two NO2s. All right, so what are the intermediates in this reaction? Let's see here. We've got, you just look at the overall and notice that the NO3 is not in the overall, so that cancels out. And also there's a note here at the bottom. You have to take the first equation twice in order to add the mechanistic steps to get the overall reaction. That just means stoichiometrically, in order for you to get the overall, you have to take the first step twice, which is not a problem because there are millions and millions of N2O5 molecules in this gas phase system. 2 times the first reaction to balance everything is completely reasonable from that point of view. All right, so actually if you took the first step twice, then the 2 NO3s would, in other words, let me put a 2 in there, 2, 2, and 2. This is just for the balance now. So then the NO3s are going to cancel, so NO3 is an intermediate. And then the other intermediate here is NO. So NO cancels, and then that's it. Now you can add, wait, there is a, let's count the NO2. You got 2 NO2s here, 1 more is 3, 2 more is 5, and then you have 1 on the left. So you got 1 on the left, 5 on the right. That's how you get the 4 on the right. One of them cancels. Maybe that one will say cancels. Okay, so then you have the overall reaction. Good to know. So the mechanism is sound from that point of view. Now what we want to do is ignore those purple 2 coefficients in the first fast equilibrium step. And now we want to use the principle of the bottleneck principle, which says that the rate of the reaction is equal to the rate of the slow step. So if the rate of the reaction is equal to the rate of the slow step, then we can say, let me write this in black here. From here, you would say rate is equal to K2 times NO2 times NO3. So that's the rate of the slow step. Okay, and that's where I pick it up on the next slide. So I repeated the mechanism, and what I just wrote down is what we've got right here. The rate of the slow step is equal to K2 times NO2 times NO3. Right, this is correct, except that it's written in terms of NO3, and we know that NO3 is an intermediate. So this right here, it's correct to write the rate law the way we did, but the NO3 is not useful to us because we cannot measure the NO3 intermediate. So we're going to use another principle in kinetics. Actually, it's a principle of equilibrium and kinetics, and it's in red here, which states that if you have an equilibrium step, the rate of the forward reaction equals the rate of the reverse reaction. So that's this step up here. We can say the rate of the forward reaction, which is going to be K1 times N2O5, equals the rate of the reverse reaction, which is K minus 1 times NO2 times NO3. And that might look a little confusing when you first look at it, but you could, in principle, take this first double-headed arrow reaction apart, and you could say rate 1 is equal to K1 times N2O5, and then the reverse reaction would be rate minus 1 would be K, that would be K1 up there, K minus 1 times NO2 times NO3. I don't know if that's helpful, but if you kind of take it apart, then you say that the rate of the forward reaction equals the rate of the reverse reaction, and that's how you get this down here. After you get comfortable with that, you don't have to write this out. You just look at this reaction, you say K1 times N2O5 is equal to K minus 1 times NO2 times NO3, which is what we have here. Okay, why did we do this? This is true, that the rate of the forward reaction equals the rate of the reverse reaction when the system's at equilibrium. Why do we care? So we can solve from NO3 here. I'm going to write this down. We can solve for NO3 here, and then we can plug it into the equation for the rate of the slow step. Remember, we said the NO3 is not useful to us. We can't measure it because it's in equilibrium. It's an intermediate. And so now if we solve for NO3 and plug it into equation 1, then we get rid of it. Okay, so in the next step here then, solve for NO3 from here. Okay, so this is NO3 is equal to K1 N2O5 divided by K minus 1 NO2. Alright, now we're going to carry that onto the next page. So think about what we're doing. We're taking this NO3 and we're plugging it in right there. We had K2 NO2 and then multiplied times NO3. So, okay, and when we do that, then we have the rate of the slow step is equal to, my pointer here, we had K2 NO2, let me back up again. We have rate is K2 NO2, and then this is the NO3 right here. So NO3 is equal to K1 N2O5 divided by K minus 1 NO2. So we just plug it all in. This is the equation for the rate of the slow step. Now we've eliminated the NO3, and the NO2s are going to cancel. I can write that down. They cancel. And then we're going to end up with the rate of the reaction, rate of the slow step, is equal to K2 times K1 divided by K minus 1 times N2O5 here. All right, and then simplify again. Next step is to say that you just take these rate constants here and combine them and say that that's equal to K. And then when we write the overall rate law, we say rate is equal to K times N2O5, where K now is going to be the rate constant for the overall reaction here. All right, so this is the answer, long-winded rather. And what do we have in the end? We see that it's first order, and we know that it's first order in N2O5. So this is the correct answer. And just to summarize, we use the same bottleneck principle in both examples. Rate of the reaction equals rate of the slow step. In example 2, we had a little problem because the rate of the slow step was in terms of the NO3 intermediate. And then we use the equilibrium step and the fact that the rate of the forward reaction equals the rate of the reverse reaction to solve for NO3. Plug in, simplify, and get the answer. Alright, there'll be another video for this first lecture, and that's going to be on the temperature dependence of the rate constant. Watch for that.